All right, so deriving the half-life equation is relatively straightforward for our integrated rate law expressions. And so the one thing that you really need to recognize is by saying half-life, what we're saying is we want the time that's required for the initial concentration to decrease by half. So that's saying that the concentration of A at some time t is equal to the original concentration divided by 2. So let's use this and plug it into our integrated rate law for a first order reaction and see what that gets us. So I'll take the natural log of, it's written as A at time t, but we're going to substitute in A at time 0 divided by 2. And then that is divided by A. That's divided by A at time 0. And this is equal to minus K times T. Okay, so all I've done is substituted in A at time T. I've substituted in A at time 0 divided by 2 for that. Okay. So then, hopefully you can see that we'll end up with A at time 0 canceling, and we'll have natural log of 1/2 is equal to minus K times T. And by doing this, we're also going to put T 1/2 here, okay, just to specify this is the half-life. So natural log of 1/2 is equal to minus 0.693. And so that's equal to K times T 1/2. And so to find the half-life, or the time required to go from an original concentration to half that concentration, we're going to divide both sides by minus K. And so T 1/2 is going to be equal to 0.693 divided by K. And this is for first order integrated rate laws, or first order reactions. Okay. If we have a second order reaction, where we have 1 over A at time t is equal to K times T plus 1 over A at time 0. We can substitute in A at time t is equal to 1/2 A at time 0. And so we'll have 1 over 1/2 A at time 0 is equal to K times T plus 1 over A at time 0. And now we're saying this is the half-life. So this is 2 over A at time 0. We're going to subtract this fraction. That's minus 1 over A at time 0. And that's equal to K times T 1/2. So if we divide both sides by K, we're going to have 1 over A at time 0 divided by K is equal to the half-life. Another way of writing this to make it a tiny bit prettier is 1 over A at time 0 times 1 over A at time 0 times K is equal to T 1/2. So here you can see that the half-life, time it takes to get to half the concentration, is inversely proportional to the initial concentration. Okay, so we can do the same thing for our zero order reaction. A zero order says that A at time t is equal to minus K times T plus A at time 0. And again, substituting in A at time t is equal to 1/2 A at time 0. So we'll have 1/2 A at times 0, and I'm going to go ahead and subtract A at times 0 from both sides. And that's going to set that equal to minus K times T. And now this is T 1/2. Alright. I'm also going to divide both sides by minus K. And so we'll have minus 1/2 A at times 0 plus A at times 0 divided by K equals T 1/2. And so we can actually say that there's a fraction in front of this A at times 0, which is 2/2. And from this, we can see that we'll have in our numerator 1/2 A at times 0 divided by K is equal to T 1/2. And just to make that a little bit more pretty, we'll do A at times 0 over 2 times K equals T 1/2. So for zero order reactions, the half-life is directly proportional to the initial concentration of reactant. So if we have a greater initial concentration of reactant, the half-life is going to be greater.